Good afternoon, everyone. Thank you for joining us. My name is Claire. I'm a contract librarian on assignment here at NOAA Central Library, and I'll be your host this afternoon. This seminar series is offered through the NOAA Central Library Seminar Program, which provides an educational forum for the presentation of ideas, research updates, and news in support of NOAA's mission. This is the second in a series on toxicity of oil, and we hope you'll join us for the next seminar in the series on August 23rd at 11 a.m. Before we start, I have a few technical tips for attendees. Just so you're aware, you are muted and you are not able to unmute yourself. However, if you have a question, you can type it into the question or chat panel, and we'll get to those during the Q&A session at the end of the presentation. If you're having any audio or visual issues, if you can't hear the speaker or see the slides, please try logging off and back on, and that will solve most issues in GoToWebinar. Just as a reminder, this is being recorded. If you'd like to revisit this seminar or view previous seminars, you can find them on our YouTube channel. Now I'm going to turn it over to Lisa, who's going to introduce our speakers today.
Hello, everybody. I'm so glad you're joining us today for the second in our 5 or maybe 6-part series, providing an overview of oil spill impacts on cetaceans. So this seminar series was born out of the Deepwater Horizon. Prior to the Deepwater Horizon oil spill, studies on marine mammals during and following oil spills were limited. I mean, we had laboratory and field studies following the Exxon Valdez, but the Deepwater Horizon oil spill disaster provided us an opportunity to do a broader scale and more longer-term series of studies, both during and following the spill. So this is a seminar series that's going to summarize these studies conducted on marine mammals affected by the Deepwater Horizon incident. And we're going to include topics such as short and long-term health effects, reproductive failure, evaluation of population statuses for nearshore and offshore cetaceans, and an overview of toxicity across vertebrate species, which, by the way, happened in the previous seminar, but is available. I think it's available now. It has been recorded. So I hope you can join us for our next seminar, which is going to be coming up on August 23rd at 11 o'clock Eastern. But right now, without taking up any more time here, I wanted to introduce our speakers for today, Dr. Lori Schwacke, Dr. Cynthia Smith from the National Marine Mammal Foundation, and Dr. Len Thomas, who's with the University of St. Andrews. And they're going to be talking today about the super cool study that they've been doing evaluating the effects of Barataria Bay bottlenose dolphins a decade after the Deepwater Horizon spill. So take it away, you guys.
Great, thanks, Lisa. Thank you all for taking the time to listen in today. I want to start by saying that while Cynthia, Lynn, and I are presenting the information, there are many people that contributed to the work. The research that we'll present was conducted by the Consortium for Advanced Research for Marine Mammal Health Assessments, or CARMA, which was a consortium funded by the Gulf of Mexico Research Initiative. CARMA had co-PIs from 7 institutions that you see at the bottom here. Key collaborators from 11 institutions, plus a number of additional researchers and professionals from over 20 organizations that supported our health assessment fieldwork. So I want to recognize their contributions and say thanks to them, because we wouldn't have been able to do it otherwise. I want to first lay out a timeline for the work that we'll be presenting to give you all a roadmap to understand the time sequence of events and how they fit together as part of the big picture of Barataria Bay dolphins. The Deepwater Horizon oil spill set things in motion in 2010. As I'm sure most of you know, the DWH spill was the largest marine oil spill in US history and obviously had huge impacts on many marine species in the Gulf, including Barataria Bay dolphins. NOAA and the other federal and state trustees conducted a natural resource damage assessment, or NRDA, to determine and quantify the injuries and then identify restoration projects. And in conjunction with the NRDA, there was also an investigation of a cetacean unusual mortality event, or UME, which was ultimately determined, at least in large part, to be caused by the DWH spill. The UME involved over 1,000 stranded cetaceans, almost all bottlenose dolphins, not because that was necessarily more bottlenose dolphins killed, but because that's the species in the nearshore areas where carcasses can be detected. Over half of those carcasses were in Louisiana. NOAA and the other trustees reached a settlement with BP in 2015, and a programmatic damage assessment and restoration plan, or PDARP, was prepared. The final settlement was accepted by the courts in April of 2016. So that's the historical background. What we'll be focused on today is what's happened since the NRDA ended. Our CARMA Research Consortium has continued the studies of oil spill effects on cetaceans in the Gulf. One of the main goals of our studies has been to resolve some of the lingering questions about long-term effects, particularly those questions with respect to health effects and how long oil-related disease conditions would last. So today, I'm going to give an overview of the CARMA studies and what we've done in Barataria Bay, and discuss the health trends that we've observed there over time. Then Cynthia is going to dive a bit deeper into the underlying disease conditions from a veterinary perspective. And then Lynn will talk about how, with these new data from the field studies, we've been reevaluating expected population recovery trajectories, and also refining analysis approaches to improve the models. In the meantime, Louisiana has been planning restoration projects, and their focus has been on projects to rebuild wetlands, including one major project involving sediment diversion from the Mississippi River into mid-Barataria Bay. Fortunately, aside from diverting sediments, the planned project will also substantially reduce salinity in Barataria Bay, which is generally not good for dolphins. So NOAA and other collaborators, including some of the CARMA collaborators, have conducted several studies to try and understand the likely impacts of those expected salinity reductions on bottlenose dolphins. These have included some tagging studies to look at dolphin movements as salinities change, and a collation of case studies from stranding network and from Navy dolphins exposed to low salinities. And those case studies provided information that fed into an expert elicitation. Based on the data and results from the studies and the expert elicitation, Dr. Lance Garrison and his colleagues did an analysis to estimate likely changes in dolphin survival rates under the different alternative scenarios proposed by the project. Their analysis and subsequent report was part of the draft environmental impact statement that was released last March for public comment. We won't be covering all that in today's presentation, but we will present some results that we've attained by integrating the results from Lance's analysis into our Barataria Bay population model. And this was something that the Marine Mammal Commission asked us to look at a few months ago, so Lynn will be showing the results of those analyses as well. So that's the plan. First, a quick refresher about what was done in Barataria Bay during the NRDA and what was found. The NRDA involved 3 different types of studies. Investigations of the stranded dolphins and tissue evaluations of those strandings, live dolphin health assessments, and photo ID studies and remote biopsy sampling. The live dolphin health assessments were particularly important because it's a hands-on sampling. We were able to do physical examinations, collect blood for routine blood work, and do ultrasound, which turned out to be really important for the diagnoses of the oil-related diseases. The photo ID was important too because we could follow individuals over time and look at survival rates and reproductive success. So the NRDA documented a number of adverse effects: lung disease likely related to the inhalation and aspiration oil exposure pathways, impaired stress response, which was observed as inappropriately low levels of serum cortisol in the live dolphins, and thinning of the adrenal cortex in the dead dolphins. There was increased mortality. I mentioned the UME, and there were also low survival rates estimated from the capture-recapture analyses of the photo ID data. Decreased reproductive success determined, again, both from the strandings and the photo ID follow-up. And all of these were summarized in a number of publications. Many of the publications were part of a special issue of Endangered Species Research that I'm showing down here if you're interested in looking into those in more detail. So also in that ESR special issue is our paper describing the model developed under the NRDA to quantify the population level effect of these injuries. It was an age, sex, and class structured population model. We estimated a baseline population trajectory, i.e. what the population would have looked like had the spill not happened, using baseline demographic parameters for bottlenose dolphins from the literature. For an initial population size, we use pre-spill population size estimates from capture-recapture or CMR analyses of data from photo ID surveys that were conducted just after the spill and reported by McDonald et al. In that same ESR special issue that I mentioned. And we constructed an injured population scenario where the population was further broken into exposed and unexposed cohorts. So the red are the exposed, the blue are the unexposed cohorts. All dolphins in Barataria Bay at the time of the spill were assumed to be exposed. Then based on analyses of our photo ID data, we estimated reductions in survival and reproduction experienced by the exposed dolphins and applied that for the exposed classes in the model. And those are reported, those estimates are reported in the publications shown there, again in the ESR special issue. Dolphins born after the spill fed into the unexposed class, and it was assumed that those animals would have normal baseline vital rates. But this was all in 2014, so we had data estimating the reduced survival and reproductive rates for the few years following the spill, but we didn't know how long the exposed cohort would stay sick. We estimated that it would take around 10 years for the exposed sick dolphins to recover based on the opinion of the veterinarians involved in the health assessments. So with this baseline and injured population model, we estimated the trajectory of the population under baseline conditions, which is the blue line you see in the graph there, and under the injured scenario, which is a red line seen there. And we established 3 metrics. First, the maximum proportional decrease, so basically the largest difference between the red and the blue lines. The number of years to recovery, which is basically the number of years it takes for the population, the red line, to get within 95% of the blue line. And then the lost cetacean years, which is the shaded area. And that's really kind of the dolphins that we were down summed over time, which is a difficult metric for people to get their head wrapped around, but it's actually a really good metric for looking at injury and for restoration options. So there were 3 important assumptions that basically drive the recovery that you see of the injured population, the red line there. Those were that the exposed class would recover over some time period to return to baseline survival and reproductive rates. Number 2, that dolphins born after the spill would have baseline survival and reproductive rates, so no adverse effects on the progeny. And then number 3, density dependent reproduction, i.e. as the population numbers went down, that reproduction rates would increase. And it's commonly believed that population growth for cetacean is at least partially controlled by density dependent factors, and there's some empirical evidence for this. So in the NRDA model, we implemented density dependent fecundity based on an extended Beverton-Holt function. And for this function, there's a shape parameter rho, for which we had a high degree of uncertainty. And as might be expected, the model analysis indicated that this parameter contributed substantially to the uncertainty in the model results. So that was all done as part of the NRDA and where we were at the end, but there were still a number of lingering questions, as I mentioned. Number 1, what are the underlying mechanisms for the reproductive impairment, and will it be permanent? We're not going to talk too much about that today, but Cynthia and Forrest Gomez will be presenting a webinar in this series in September to delve into that in more detail. Other questions were, will the dolphins whose health was impacted by the oil spill ever recover to a normal health state? Will there be effects on the next generation? What are the appropriate parameters for density dependent growth? And that was what our GOMRI research set out to address. But how did we do it? Well, we continued the Barataria Bay health assessments, adding new diagnostic techniques, primarily new ultrasound techniques, which were developed using the Navy dolphin population. And we then continued the health assessments in 2016, 17, and 18. We paired those with data from health assessments conducted by Dr. Randall Wells, one of the CARMA collaborators, with his program in Sarasota Bay as a comparison site. We conducted photo ID studies to document the continued documenting reproductive outcomes. And we integrated these new data and developed refined analyses and models to better understand population recovery trajectories. And I'm gonna, or Lynn's gonna talk about the Barataria Bay population model today, but there will also be another webinar in this series, 2 more webinars in this series, one in August by Tiago Marsh and Lynn Thomas, to talk about the offshore models for the offshore species, and then Lance Garrison in October to talk about the coastal species. And then also in 2019, there was a collaboration with NOAA where they wanted to do extended capture-recapture surveys in Barataria to inform the restoration planning and EIS. And we participated in that. I mean, part of that was to get updated abundance estimates. It also allowed us to get additional follow-up data on our health assessment animals. But it was really cool to get another abundance estimate in 2019 that we could compare with our model predictions to see how they compared. And Lynn will talk more about that. So one of the analyses tools that we developed to compare the health of live dolphins sampled between the oiled and unoiled sites was Prognosis Index. And we've continued to use that to monitor population recovery over time. With the hands-on health assessments, as I mentioned, we conduct a comprehensive suite of diagnostics that you see here. And a number of different indicators of health. But the prognosis scores from the vet team allow us to boil down that information into a single informed indicator of the animal's health for comparisons. In a normal healthy population, we'd expect to see mostly good and fair prognoses, maybe a few guarded conditions, but poor grade prognoses would be relatively rare. So for examining the temporal trends and population health following the spill, we use the prognosis indices, but we also wanted to distinguish between the dolphins that were alive in Barataria when the spill occurred and presumably exposed to oil versus those progeny that were born after the spill. As I mentioned, those are important for our models as they're 2 separate classes in the population model. So to get at this, we went back and examined photo ID histories to identify which dolphins were in the bay at the time of the spill, and then also ones for which we observed their birth after 2010. And we did a similar analysis in Sarasota Bay. We then applied a generalized additive model, or GAM, to examine the effect of time and site for both cohorts. And this is what we found. So what you're seeing here is using the prognosis scores over time. The graph indicates the probability of a guarded or worse prognosis. And on the x-axis is year for all of the dolphins that were alive pre-spill or alive at the time of the spill. And then all of the dolphins born after the spill are pooled into this last bar because we didn't have enough over time to break them out over time. So we pooled all those into one cohort. And then we use the GAM to look for a temporal trend. And as you'll see, so yellow is guarded, red is poor, and the darker red is grave. So the darker the red, the worse the prognosis. And you'll see that in 2011, there was many guarded or worse prognoses. It looked like it was going to start to get better, and then started to go back up again, particularly in 2018. We had a really high probability of guarded or worse prognosis, and this was a significant trend. If we compare that to Sarasota Bay, we see, not much of a temporal trend, and in general, a much lower probability of guarded or worse prognosis, and in fact, no poor or grave prognoses in the older animals born prior to the spill. For the animals born after the spill, so in Sarasota, born after 2010, fairly similar numbers or proportions as we saw in Barataria Bay. So from this, we gather that the health of dolphins that were in Barataria Bay at the time of the spill versus the dolphins in unoiled Sarasota Bay was significantly worse, with a really significant p-value, but that the health of dolphins born after the spill between Barataria Bay and the unoiled comparison site was not really that different. So to summarize population health trends over time, the health of pre-spill dolphin cohort in Barataria Bay has not improved and likely has worsened in the decade after the spill. And this could be related to an aging cohort, progression of chronic disease, which Cynthia is going to talk a little bit more about in a moment, or increased susceptibility to other stressors. Although we did look for evidence of new emerging stressors or increase in other stressors, and we didn't find evidence of this. We also found that the health parameters for the post-spill cohort, animals born after the spill, appear to be within normal range. There's one caveat to that is the immune parameters. And Dr. Sylvain de Geese, who was also part of our CARMA consortium, published a paper this year on the immune parameters, and he did find perturbations in the parameters for the post-spill cohort as well. So whether those are conditions that just haven't manifested as disease yet, we don't really know. It was from the slides that you saw, it's a short monitoring period in general for animals born after the spill, and relatively small sample sizes. So we're not super confident that this is going to hold forever. So with that, I'll turn it over to Cynthia and let her talk about the veterinary aspects of this.
Okay, great. Thanks, Lori. And yeah, just to begin, we are going to take that poor health picture and dissect it out just a little bit. And one of the bullets that Lori had on the previous slide was this chronic progression of disease. So we're going to explore that a little bit with the persistent lung disease picture that has developed for us. So next slide. I think we have a little bit of a lag. So I'll try to say it a little early for you, Lori. Thank you. So if we start by talking about exposure, and we really start to think about pulmonary disease and the potential routes for exposure, we have to go back to the spill and think about the fact that prior to Deepwater, a lot of scientists largely believed that marine mammals would actually avoid oil. This did not prove to be true, and in fact, over 1,000 animals from more than 10 species of dolphins and whales were seen and documented swimming through the oil. Next slide. So knowing that and having documented that, then we start to think about how could the animals actually have been exposed and absorbed oil. So there's multiple different routes for a marine mammal to then absorb the oil. One is through inhalation, so inhalation of either the vapors or the aerosols, or aspiration, which is basically just breathing in droplets, oil, liquid or droplets into the lungs. They can also ingest the oil and then it can get absorbed in the GI tract, or they can actually ingest it, become nauseous, vomit, and then aspirate that vomitus, and that would cause some pretty severe disease. And then dermal or ocular contact is also a possibility, a little bit less concerning when we're talking about pulmonary disease, but it could also be an issue. Next slide, please. Okay, so in addition to that, in addition to the fact that we have the animals within the oil spill footprint and exposed to the oil and likely being exposed through more than one pathway, we also think about the fact that marine mammals in general could potentially be more susceptible to the toxic effects of oil just based on their physiology. So when we think about the way dolphins breathe and whales breathe, they're taking in this rapid intake of the surrounding air directly into their lungs. They don't have protective cilia or nasal turbinates like other mammals do, so that just when they breathe in, it goes right into the lung. There's about a 90% exchange of deep lung air. Wasn't quite ready, but that's okay. Deep lung air, thanks, Lori. And then they have an extended breath hold. So they're diving with the air filled in their lungs. And then they also have a double layer capillary bed. Go ahead to the next slide. And those double layer capillary beds actually can enable that movement of compounds into their lungs. So there's a lot of things with their physiology that could be setting them up for increased risk. And then in addition, marine mammal behavior, especially in the bay sound and estuary stocks, may actually also increase their exposure. And when we look specifically at the Barataria Bay dolphins, many of those dolphins were actually, during our health assessments, were satellite tagged. And this was in order to track their movement. We know from the studies that the animals actually have what's called high site fidelity, which means they're unlikely to leave, and they may actually stay in the same area for many years, or perhaps for even their whole life. And so the map on the right, each little dot there, each black dot is actually a moment in time for a dolphin that's been satellite tagged. And so you're seeing all the different tracking positions for Barataria Bay dolphins that were satellite tagged and you can see how tight and how small the range is for these animals. Next slide. Okay, so now we've established that you know, the animals have these routes, these potential routes of exposure. Their physiology and their behavior may set them up to be more susceptible. So what did we actually find? And through the course of the NRDA investigation, we did actually document that dolphins living in these heavily oiled sites, specifically Barataria Bay, but also Mississippi Sound, had evidence of poor pulmonary health. So in 2011, the first year that we were able to do the live animal health assessments, the dolphins in those oiled areas were about 5 times more likely to have moderate to severe lung disease. And then in 2013 and 2014, which was the latter part of the NRDA investigation, it got slightly better. So if you remember, those prognosis scores were also getting a little bit better during that time, but they were still not good. And so we still had a 3 times more likely, the dolphins, excuse me, were 3 times more likely to have moderate to severe lung disease in those oiled areas than in the unoiled areas. So the big question for us was this going to persist? Would the lung disease actually start to show evidence of improvement? Would it stay the same, or would it get worse? And so next slide. And so that's when Lori has already described our capture release health assessment technique that was used in order to do live animal health exams. And the photo on the left is showing a pulmonary ultrasound examination in progress. And those white goggles are the virtual reality headset goggles that we use to project the ultrasound image into the goggles so that the sonographer can actually see what's happening inside the animal. And then there's an operator, Veronica Sendejas, is actually right behind me, and she's actually operating the ultrasound machine. It's a very common way that marine mammal clinicians use to evaluate the health of dolphins, both wild and those in human care. And we developed those techniques for this specific project with the Navy dolphin population, as Lori mentioned. Okay, so let's move on to the results. Next slide. And so if we look at the pulmonary ultrasound evaluations that we were able to conduct, we evaluated 103 dolphins in Sarasota Bay, which was not impacted by the oil spill, and 171 dolphins in Barataria Bay. And we really wanted to focus in on those animals that were alive at the time of the spill. So Lori's already gone into the fact that we were able to assess whether or not that animal was alive during the time of the spill, or if they were born after. And if they were born after, then those are different questions that we're asking of that group of animals. So for this portion of the study, we're really focusing on those animals that were alive at the time of the spill and may have been exposed. And then there were some animals that were borderline, and we just didn't feel comfortable classifying them. They were too close to call in terms of were they in utero, or were they actually born, or were they just a thought in the mind of the dolphins. So we did not classify them, did not include them. So for those animals that were alive during the spill, we then looked at the comparison of findings between the oiled and the unoiled sites. Next slide. So we're going to be looking at some heat maps that are structured by pulmonary abnormality. And if you haven't seen any of this data yet, you may not be familiar with the kinds of abnormalities we're detecting with ultrasound, but just to give you a quick snapshot of that, very similar to human medicine, we're looking for things like pleural effusion, which is excess fluid, nodules, masses, something called alveolar interstitial syndrome, which is when fluid and cellular infiltrate starts to work its way into the lung for a variety of reasons and reduces the air, so we can detect that. And then consolidation, which is not good, and that's where that fluid and infiltrate has now actually progressed to the point where the lungs are consolidating. So those are the kinds of things we can actually detect just within a few minutes with an ultrasound exam. Next slide. And then in addition to detecting those abnormalities, we also wanted to give it some kind of objective score for what was the overall pulmonary health for that animal. So this is something we actually developed for the Deepwater Horizon investigation, and we wanted to have an objective way to compare dolphin to dolphin. And so we basically looked at the number of findings and the distribution of findings to figure out where did these animals how did they compare to each other? And we came up with a scoring system that ranged from normal to severe. In general, healthy populations and the Navy dolphin population, they fall in that normal to mild lung score category most often. It is the moderate to severe where we're really starting to be more concerned about the lung disease component of that animal's health. And we're going to be talking just for a few minutes about that moderate to severe lung score and what it meant for the Barataria Bay dolphins. Next slide. Okay, so to get to the results, we're going to look at just a few heat maps and then we'll wrap this part up. But basically, what we're going to be looking at is the prevalence of these different pulmonary abnormalities in the Sarasota Bay dolphins versus the Barataria Bay dolphins. And we're going to look at it by year. So on the y-axis, you see the years going from a 2011 to 2018. And the color, the light yellow to dark red, represents an increase in prevalence. And so this is Sarasota Bay. And you can see that most of the map is light yellow. We have a little bit of darker orange and just barely getting into the red zone with nodules in 1 year. But for the most part, we're just not seeing a lot of pulmonary abnormalities in Sarasota Bay. And when Lori clicks the next slide button, it's going to dissolve into Barataria Bay. So watch the colors as they change. And basically, you can just quickly see that we're starting to have more of that dark orange, red, and dark red color, which just means there's an increased prevalence of some of these findings, very specifically the nodules, also the consolidation, the AIS that's showing up in Barataria Bay. And very interestingly, as Lori pointed out in her prognosis slides, look at 2018. So things are actually getting a little bit worse in Barataria Bay with time instead of better. Next slide. And then we also, in addition to looking at those pulmonary abnormalities, we're also looking at the lung scores. And so this is Sarasota Bay, and we're looking at in yellow the prevalence of moderate lung disease in Sarasota Bay, and the red is severe lung disease. And it's structured the same way as the prognosis slides that Lori already shared are. You can see on the x-axis we have the years, and then that last bar in the post-spill, that's just the animals born after the spill. We're not as concerned about them right now, at least not for this portion of the investigation. And then the prevalence is on the y-axis. So you can see we do have some moderate lung disease cases in Sarasota Bay, but we don't have any severe cases in the animals that were alive at the time of the spill. Now she's going to press next slide, and you're going to see that dissolve into a Barataria Bay map. And the biggest takeaway here is look at the prevalence of severe lung disease. So we did not have any cases of severe lung disease in those born at the time of the spill or alive at the time of the spill animals. We have quite a bit of it, and this was significant. So we don't have the p-values on here, but we do know that this was statistically significantly different than Sarasota Bay. And so what we're seeing is something that we believe is very important in contributing to the overall poor health of the animals. Next slide. Okay, and I'll just quickly mention that there are some clues for us about what does this actually mean, and can we take this a little further in terms of trying to understand why is the lung disease getting worse. And so we're tracking something that is the distribution of the alveolar interstitial syndrome, or AIS, and how it looks in the animal. Basically, there's something that we're calling worsening AIS that is from dorsal to ventral or back to belly. And that can be consistent with different kinds of disease states. And so we're seeing an increase of this pattern, this distribution of AIS in dolphins. And it's the prevalence of that pattern is increasing. So this is something we're focusing in on now, and we'll be talking about that more in the future, but it does give us good information about the etiology and the actual pathway of the disease progression. So we're focusing on that now. Next slide. Okay, so I'll just wrap it up by summarizing. We're gonna skip over the case example, Lori. You'll see some pictures go by. This is just a dolphin that actually had severe lung disease. These are the ultrasound images from that animal, and the histopathology confirmed what we saw in the live dolphin because the animal died and washed up dead. So it's just an example of how we were able to ground truth our data, especially during the NRDA, in the bodies that washed up. And in that case specifically, it was the same dolphin that we then were able to, unfortunately, necropsy and confirm these findings. So the pulmonary ultrasound findings overall in Barataria Bay since the spill are showing us that pulmonary disease is persisting, at least for the 8 years following the spill. And we're still at that about 3 times more likely to be diagnosed with moderate to severe lung disease in Barataria Bay than in Sarasota Bay. We have this high prevalence that was documented in 2018. So again, it looks to be getting worse. And we do know that pulmonary disease, the picture is contributing to poor overall health. And we're going to be talking about the reproductive impacts in the future during this series. Next slide. So in general, the takeaways here are that the health effects in dolphins are consistent with the known impacts of oil. There's also some really interesting studies coming out of the NIEHS Gulf study and the Coast Guard cohort study, and our findings are consistent with the human respiratory symptoms that are being reported. So we're paying attention to that. We've also ruled out other known causes of increased lung disease. We didn't have time to get into all of that, but we have no evidence that this lung disease is due to things like morbillivirus, dolphin morbillivirus. We do believe it's connected to the oil. And finally, we do really need to continue to monitor these animals to really understand the true trajectory and how is this story going to really play out when it comes to pulmonary health and overall health. So with that, I will turn it over to Len. Sorry, Len, I went a little bit longer than I expected, but now over to you.
No problemo. Claire, could I take a copy of the screen? Thanks. Let's see if this works then. Okay, so hopefully you're seeing the screen now. Does that work? I'm going to guess yes.
Yep.
Great.
Yes.
Okay, thank you. So I'll present the modeling work that we've done to put this together, building on the model that Laurie led for the natural resources damage assessment that was published in 2017. But it was a team effort, so I'd like to pay tribute to the other modeling project team members. And also to the whole CARMA team who kindly allowed me into the field to see Barataria Bay dolphins. Here's the one picture of me in the field for the one day I made it before I got hit by a stingray and had to go do some modeling, which is what I'm much better at, and spend the rest of the time on these Zoom calls with everybody talking about modeling. Lastly, there's a spatial capture-recapture analysis in here that was led by my colleague Richard Glennie that we'll get to. Okay. So what did we change as a result of the information that the updated information that we had? So one thing we did was that based on this finding that the dolphins do not seem to be recovering, or at least some of them do not seem to be recovering, instead of previously having an exposed cohort that recovered and asking how long it took them to recover, we instead split the exposed cohort into two, one group that don't recover in their lifetime and one group that do recover in their lifetime. And then an appropriate question is, what proportion of the animals that were exposed and alive at the time of the spill recover? And to answer that question, we turned to expert elicitation. So this is a formal procedure of presenting information to experts and then eliciting from them a probability distribution. And so we prepared a dossier for our experts. This is a picture showing experts and facilitators. This is in San Diego at the Southwest Fisheries Science Center where we had this meeting. We prepared a dossier based on everything that we knew at that point about recovery, based on the kind of thing that Cynthia's just presented to you. And then we asked them for this, what's the probability that an exposed dolphin would recover from guarded poor or grave through to a better prognosis in its lifetime. And this is the probability distribution we got out of that. So the mean is about 0.18 or roughly 0.2, but you can see there's quite a wide uncertainty in that probability. And then that feeds through into the simulation of the population trajectory. The other thing that Laurie mentioned is that there was a density-dependent component to the model, and that the uncertainty on the shape of that density-dependent function was a big contributor to the uncertainty in the output in our previous round of modeling. And so we held a second expert elicitation where we asked a group of population modelers, we presented all the information we could find about demography of cetaceans and long-lived species in general, and asked for their opinion about this row parameter, which is quite a hard thing to elicit, as you can imagine. So we made a tool that helped think about what this row parameter does and what effect it has. And what I'm showing here is this is the distribution we had before on that parameter, and this is what we got from the elicitation. So the row parameter was thought by the experts to be rather larger, and this below is what it means. So this is kind of some simulated trajectories from previously from the NRDA, and this is what they look like now. So you can see the population, as population size goes up, the fecundity stays high a little bit longer and then falls a little bit steeper, and there's a bit less uncertainty in how that's going to happen. So that's what we got for that parameter. We also, as Laurie mentioned, had some updated capture-recapture data that we could use from 2019, but also the methods have considerably improved. And this is some work by my colleague Richard Glennie. We reanalyzed the capture-recapture data, which gave us a much better picture here of where the animals are in Barataria Bay on average. So this just shows mean density estimated from those data. This area here over to the east was surveyed for the first time in 2019. But also we got a much better estimate, or yes, better in some sense of survival, how that changes through time, which is what you're seeing here. It's better because we were able to fit a smooth to that through time, but also to what we call model average, which means we allowed uncertainty in the amount of smoothness to feed into this analysis. So we think this is a lot more robust than what we had before. Unfortunately, you can see that there's quite a lot of uncertainty in this first time period as to what survival is. And that's going to be absolutely critical, because that's the major component of damage is decreased survival. And so not knowing very certainly what the decrease in survival was in the first time period is going to cause a lot of uncertainty in the results. We also got updated abundance estimates, and we assumed that the pre-spill abundance was effectively equal to the highest abundance that we observed, which is these periods here. What's happening in these earlier periods is that because of all the activity in Barataria Bay, dolphins are pushed out beyond the area that we were able to do photo ID in. And so the animals are there in the bay, but they're not part of our study. So that's why we took this estimate, which in itself is probably an underestimate of the number that were there before the oil spill, because some have died. So if anything, we're going to underestimate the damage this way. We made a bunch of other updates to the population model, and I don't intend to spend a lot of time on them because they're less important in the result, but we changed the way we calculated the pre-spill survival to one that we think is more reliable. We also looked again at a model parameter about age at sexual maturity and updated that based on data that we gathered in a meta-analysis, and we also allow for uncertainty in that, which we didn't before. And lastly, we assumed before that there was reproductive senescence, but we didn't this time. It makes almost no difference to the animal because the trends, because there are very few animals that are that old. Okay, let me just cut to the chase and show you the results. So this is what the predicted population trajectories look like. This blue line is under baseline scenario, so without the oil spill. This is the initial population size from the spatial capture-recapture analysis. And then this red, and there's uncertainty is shown in this band here. And then this red line is with the oil spill. So that's our estimate of what's actually happening with, as you can see, quite wide uncertainty on that. This is a 95% confidence interval. This is where we are about now, 11 years after the spill. So we're thinking that we're just turning the corner and population is starting to recover. This is the spatial capture-recapture analysis from 2019 that's independent of this projection. So we didn't use that directly in making this projection. And as you can see, our prediction is not too far away from our estimate of what's really out there. And I can discuss the difference, but the confidence intervals on these things overlap. So functionally, they're extremely similar. And as Laurie mentioned before, we calculated some damage metrics. So here they are. The maximum size of the maximum proportional decrease between the baseline and the impacted trajectory, the number of years to reach 95% of what we think would have been there on the baseline, and the sum of the difference between these two, the number of lost cetacean years. So we're saying we think 44% maximum decrease, around 35 years to recovery, and 31,000 lost cetacean years. And these numbers are actually really quite similar to the numbers that we published in 2017 before we had all this extra information. which made me feel great in one way because all of those guesses that we made back then seem to have played out now. But then it's also a little depressing in another way because we've done an awful lot of work since then and it doesn't change the picture very much. And indeed, it is going to take many decades before the population recovers. One very important component of the kind of analyses that you must do under these kind of situations is look at what's causing the uncertainty. And so we did some sensitivity analyses. This left-hand plot shows if you keep every parameter constant except sampling from the uncertainty on one parameter, what effect does that have on the uncertainty in the output? And what you can see here, sort of glancing at it very quickly, is that uncertainty mostly comes from this parameter here, which is the first year after oil spill survival. So like I was saying before, there's quite a lot of uncertainty in what the survival was directly after the oil spill, and that's feeding through to produce quite a lot of uncertainty in the damage metrics, in the injury metrics, which really highlights the importance of doing as much as possible to get an accurate survival estimate right after an environmental disaster. This is usually pretty difficult to do in populations that aren't monitored before the disaster with photo ID, because you need to build up a photo ID catalog, and those initial estimates tend to be less precise than ones that come later when you built up a bigger catalog. So it's a great lesson for future damage assessments is to get a lot of field work done straight away, if at all possible. This right-hand one is what we call elasticity. So this says if you change a parameter by each one of these parameters by 1%, what percentage difference does that make to the injury metric? And so it's a bit different from this one, because this one, if there's a parameter that has a lot of uncertainty in it, but changing that a bit doesn't make much difference to the answer, in other words, it's not very elastic, then it's not important. So this kind of confounds how much uncertainty you have in your metric versus how elastic it is. But what you can see from this, for example, is that this is baseline survival. So baseline survival is very elastic. If you change it, it makes a big difference to the answer. But there's not a lot of uncertainty coming from that because we knew we had an estimate of baseline survival that's pretty good. Whereas adult survival first year post-spill is quite elastic, and indeed there's quite a lot of uncertainty coming from it. I could talk for a lot more about these different things. I'm very interested in it, but I'd better move on in the interest of time. To talk about what do you do with these kinds of things. So this is just an example of an application of these kinds of population models, and it's looking at what a restoration plan might do for the population going forward. We have this population model, and we can plug in different values to say what would happen if, let's say, survival changes in the future. And so this is, as Laurie mentioned earlier, the mid-Barataria Bay sediment diversion, where the proposal is to release fresh water coming down the Mississippi and the associated sediments into the top of Barataria Basin during seasonal flood times in order to attempt to restore the marshland to a more natural situation and help prevent coastal erosion. But it will also inject a large amount of fresh water into the bay, which will be bad for dolphins. So the plan is a 50-year project. And sorry, here are some dolphin sightings from the most recent photo capture-recapture, and just an approximate density surface showing that most of the dolphins are down here. And there are 4 strata here. There's a west, central, southeast, and barrier island stratum that I'm going to refer to later. The Marine Mammal Commission organized a seminar session on the effect of low salinity on bottlenose dolphins back in March. That's still available online, so you can see the talks that went on there. But just to sort of give a précis of some of them, Laurie gave a talk on what we know about the population in the bay and how it's recovering of dolphins. A colleague, Ryan Takashita, gave a talk on what is liable to happen, what we think might happen to the dolphins in terms of their movements and so on when the fresh water comes. And this is based on satellite tagged animals combined with a salinity model, so we could estimate what the salinity was like in the areas where these dolphins were sighted. So these little dots here are sightings of dolphins. And also combined with some health assessments that were specifically done in areas where the salinity is low. So what you can see here, this is just an example for some dolphins, but their home range is relatively small, or the area that they moved in during the time that the tags were on, which is several months, was quite small. And these colors tell you what the salinity we think was at the time. And there's really no evidence that animals moved in response to low salinity. They stuck in an area and they didn't seem to, when they moved, they didn't seem to move in response to low salinity. Animals under low salinity develop skin lesions and also have other health issues, and that was found in the health assessments. A colleague and I, under a separate piece of work, ran an expert elicitation on what the survival implication is of being for extended periods if you're a dolphin under low salinity scenarios, and this is one of the outputs from that. So this is an expert elicited estimate of survival or survival multiplier. So 0.5 means half the survival of natural conditions or baseline conditions, against how many days, continuous days, you're in low salinity water for. So the probability of survival is estimated to be 0 after 75 days, but you can see there's quite a bit of uncertainty in that. So Cormac Booth, who led that expert elicitation, gave a talk on that. And then Lance Garrison gave a talk on the implications of that in terms of survival in Barataria Bay from the proposed diversion project, Mississippi diversion project. He split the population into these 4 strata that I showed you earlier and looked under the no action alternative, which is no diversion at all, what the effect of low salinity would be on survival, taking a simulation approach where he put animals down in proportion to their estimated density, allowed them to move around in a facsimile of what we saw from the tags, and then used a hydrographic model to accumulate low salinity through a day-by-day basis, and then read off the numbers of days of low salinity against this expert elicited function to work out what the survival would be. Did that lots of times, simulating from uncertainty on the inputs, and came up with these numbers. And this is under the no action alternative, these ones here, and this is under the so-called applicant's preferred alternative, which is the sort of most preferred proposal for how much a diversion there would be in practice, a river diversion there would be in practice. So there's quite a bit of uncertainty here. I should say that this doesn't take into account uncertainty in hydrography. So it's for one example year, and I can talk more about that later if there are questions. Or we can ask Lance too if he's listening in. So those were the talks, and after the talk, we received a letter from the Marine Mammal Commission saying, well, effectively, Dr. Schwacke gave a talk about population modeling, and Dr. Garrison gave a talk about survival changes, so could you please put those 2 together and work out what the population change is going to be as a result of the proposed diversion? So that's what we did. We split the population into these 4 different strata. We assumed that animals don't move between strata because we have no evidence that they do. And then we took these estimates of survival and sort of backed them off against our baseline estimates of survival to make projections about what would happen. So this is the results for those 4 strata going forward 50 years, which is the planned length of time of the diversion. The black line here is the recovery trajectory under no action, and the red one is under the applicant's preferred alternative. And you can see effectively that in 3 out of 4 of the strata, the population goes extinct, or the animals there go extinct. And in the island stratum, which is the one furthest down towards the Gulf proper, the population decreases quite a lot. And after 50 years, our estimate is that there'll be somewhere between 100% decline and an 80% decline. So a drastic effect overall. You can read more about this because the report that we put together in response to the letter from the Marine Mammal Commission is available on their site. So please have a look there if you want to find out more. Okay, so then to wrap up. So a decade after the spill, as Cynthia has shown you, disease conditions persist. They're worse there than they are in a comparison site, and they've also recently worsened in dolphins exposed to the spill. Dolphins born after the spill are, however, in better health. We think that the population is at a minimum point about now. It's about 44% lower than it would be if the spill hadn't happened. It'll take decades to recover, somewhere between 2 and 6.5 decades. And the new information that we've gathered under this KAMA project has corroborated the predictions that we made in the original damage assessment. And lastly, looking at this sediment diversion proposal, we estimate it'll cause about a 96% decline in dolphins in the bay over the 50 years that it's planned to take place, compared to what would happen if you didn't do that. There are some lessons for future damage assessments. And so we feel our work demonstrates a really nice framework for integrating different studies together to form a sort of holistic population assessment of what we think is happening. It's a nice demonstration of integrating diverse information together using expert elicitation. It highlights the importance of precise estimates of survival for these long-lived species, at least straight after a disaster, and also the importance of long-term health monitoring to find out what's happening and whether animals are recovering or not. And with that, I'll stop. Thank you very much.
Thanks, Len. So we do have questions. If there are any additional questions, please type them in the question panel. We'll get to as many as we can. If we do go over time and you have to leave, you'll be able to find a recording of this seminar on the NOAA Central Library YouTube channel tomorrow. And any questions we don't get to at all will be emailed to the presenters and they can follow up with you at a later time. So it looks like our first question, correct me if I'm wrong, but I believe this one is for Cynthia. Would the increase in 2018 in lung disease be an indirect impact of climate change and the increase of CO2 in the sea?
Okay, so good question. So are the impacts we're seeing that, Lori was showing the prognosis scores slightly getting better and then getting worse again. And then we showed the same thing happening with the pulmonary health scores. So the question is, could there be other factors contributing, like climate change, to that, what's going on in 2018? And we are using all these same measures we're being very consistent in our techniques to evaluate the lung disease. So we're looking at it in the same way, but there absolutely could be other factors contributing to the overall health picture. And then we're looking at more of a multifactorial issue. However, we are still looking at Sarasota Bay. We are still comparing the results in Barataria Bay to the non-oiled site. We haven't stopped doing that, and we're not seeing that happen, certainly not to the same effect in Sarasota Bay. And so that gives us a really nice way to compare the changes that are happening. So again, it's possible that we're seeing other factors starting to contribute and may have the whole time. But the great value of comparing the animals in Barataria Bay to other sites is exactly that. So we do think that this is still linked, at least in part, if not completely, to the oil exposure. Lori or Len, would you like to add anything to that?
I'll just say that if you notice in the prognosis graph in Sarasota Bay, it wasn't really a significant increase in 17-18, but it gone up slightly. There was a harmful algal bloom, or there was a series of harmful algal blooms those years in Sarasota Bay, and that's what we think may have contributed to a slight uptick there. But again, nothing to the effect that we saw in Barataria Bay.
Yeah, and I guess I'll just end with the fact that we do take all of the data into account when we're looking at the overall health picture and the prognosis score. So those are a little bit more of a cumulative measure in terms of the veterinarian's perspective than just those single other measures like the ultrasound scores. So those prognosis scores we think are quite valuable.
All right, thanks, Cynthia. The next question is, I understand you see significant pulmonary lesions related to the oil spill, and you mentioned effects on reproductive health. But have you seen renal disease associated with the oil spill too, such as AKI soon after the spill, and then CKD in subsequent years?
Great question too. So are we seeing evidence of renal disease? And are these things that we could pick up? That would be a question I would have. Could we pick these things up in a blood sample, a urine sample, or an ultrasound exam? Some of the things like chronic kidney disease, you would be a little bit difficult to detect just in a snapshot of time. Easier to detect likely in a carcass. And so we do, in the beginning, during the NRDA, we actually have a lot of data from the dead animals that were washing up. We have a lot less data in the 2016 and on years, in part just due to we don't have as much of a stranding response in place right now in Louisiana, which we really need. And so we don't have as much histopathology to help answer that question. So I would lean a little bit more on the histopath than the live animal studies, unless it was very obvious. And we were not seeing evidence of renal disease in the dead bodies, and we were not picking up like high UBN, high creatinines, or evidence of hydronephrosis or anything like that on the ultrasound exam. So we were not picking up any significant renal disease. We did pick up adrenal disease, and so there's a lot of information on that in our publications. If you specifically look at Lori's publication from 2014 about the health assessment findings, and then the 2017 publication from Smith et al., then you will get to read a little bit more in depth about all of the veterinary findings that were captured.
Thanks. So we are at time. I just want to remind everyone, if you do need to leave at 3, this will be on the NOAA Central Library YouTube channel. And I do want to be respectful of everybody's time, so I'm just going to ask one more question, and then any questions we don't get to will be forwarded to the speakers and they can follow up with you. So our last question today is, how did the oil spill happen? And is there anything we can do as individuals to prevent oil spills in the ocean?
One for you, Laurie.
Actually wanted to pull Lisa DePinto back in there for this one. Yeah, I mean, there's a whole seminar I'm sure that could be done on how the oil spill happened, and what we can do. You know, look for alternative energy scenarios. Yeah, I don't know. That's a great question. Lisa, are you on? There you go.
Alternative fuels. I'm probably not supposed to even answer that question in my area. So but it's a great question, and you know, I think there are a lot of ways we can cut down on our consumption of these kinds of products. So that's something we personally can do, and I don't want to get political. So I mean, I do want to get political, but I won't. So.
I would just add to that. Oh, no, you go, Len. You go.
No, I was going to change the subject slightly, so go ahead first.
Okay, all right. I was just going to say that one thing that I think we can all do, and what the seminar is doing today, is making sure that our science gets to the people that it needs to get to. Like, we as scientists can generate the science, we can study the negative impacts of these disasters, but we can't be the ones to actually then change policy and influence all those decisions. So this is wonderful because our science is actually getting even more broadly shared with seminars like this. And so, you know, for those people that are on the call that might be in policy or are policy makers, we're more than happy to always share our science, and we have lots of resources so that can help people become as educated as possible to make great policy and decisions. Len.
Yeah, great points.
Yeah, I guess my point was quite similar in the sense that just to point out that there was considerable uncertainty in the projections that we've made. And the main reason for that is that, to be frank, there was completely inadequate monitoring going on of the Gulf, despite the fact there's all this oil extraction. And one of the big messages, I think, from us is, if we are going to be doing these dangerous things, then we really need to be monitoring what's going on so that we can pin down when there is a problem as fast as possible. And so, relevant to that, if we're planning on restoration efforts that might affect, for example, dolphins, we need a really decent monitoring program in place so that if there is a problem, as we're predicting there might be, we can find out as quickly as possible.
Yeah, and our Office of
Oh, I'm sorry.
Oh. I was just going to say, our Office of Response and Restoration continues to do research and methods development that's going to advance our ability to respond better, quicker, faster, and do better assessments so that we can ensure better restoration on the ground. That's kind of not really answering the question, but it's worth noting. So these scientists here, the scientists you're going to be hearing from in the rest of the seminar series, and you know, our Office of Response and Restoration, we're really dedicated to trying to get better at prevention, response, and assessment associated with these incidents.
Thanks, Lisa. So that is all we have time for today. I just want to thank all of our speakers, and thank you all for joining us. You'll be able to find this presentation on YouTube later this afternoon or tomorrow. When the presentation ends, you'll see a survey. If you could take the time to fill that out, we do use those surveys to improve marketing our library seminar service and to inform future seminar topics. Thank you all again for joining us, and have a safe and enjoyable rest of your day.
Thank you, guys.
Thank you.
Thanks.
Bye, folks.